Hi guys, welcome back. In this video, I will continue talking about mechanical properties of metals, and also I will carry on with the second topic in this module, which is the material failure. So another material properties that I would like to introduce, or you've probably already been introduced with these material properties, is Poisson ratio. So to explain Poisson ratio is probably the best way is for us to look at how material behave. Like for example, this rubber band here. If I stretch this rubber band in its longitudinal direction, obviously what you can see is that this material is going to elongate and it's going to stretch, and in this direction it is going to elongate. But you can also see that its lateral direction, these materials also deform. It is actually contracted in this direction, in its lateral direction. So is this what Poisson ratio is all about? So Poisson ratio is the properties of materials that will tell us how much the material will deform in lateral direction. So if you look at this cube here, if I apply longitudinal force, axial force, tension force to these materials, what is going to happen is in X direction, it is going to elongate. But you also have to realize that in Y and Z direction, it is going to contract it. To define Poisson ratio precisely, let's take a closer look to the cube when we apply tensile force. So Lx, Ly, and Lz here is the original dimension of the cube. Delta Lx, delta Ly, and delta Lz are the changes in this dimension after the load is being applied. Now we can write up our strain in all of these three directions. Just a quick reminder, strain is defined as the change in length divided by the original length. So when we applied our tensile force, it turns out that resultant strain in the lateral direction are equal, and they are proportional to the strain in the longitudinal direction. So the ratio between the longitudinal strain and the lateral strain is actually a material constant. And we denote this material constant with the Greek letter mu. And this is, as you can guess, is the Poisson ratio. So Poisson ratio is unique for homogeneous and isotropic materials. So you can't use this definition or this analysis for materials that is an isotropic. The materials must be having the same properties in all of, if you measure it from different direction. And why is it in negative sign? It is because the longitudinal elongation caused lateral contraction, which is a negative strain. And also, you have to remember that lateral strain is the same in all of direction, and Poisson ratio is dimensionless, and normally metal materials will have a Poisson ratio in between 0 to 0.5. So apart from the tensile test that we were talking about yesterday, where we can compute stress and strain diagram, when a specimen is subjected to torsion test, a shear stress versus shear strain diagram can be developed. So the raw data that you will get from torsion test is the applied torque and the angle of twist. And from there, using the torsion equation, you can derive the shear stress and the shear strain. And when you plot that data, you will get the shear stress and versus shear strain diagram. So this is the example of the shear stress versus the shear strain diagram. And from this diagram, material will exhibit linear elastic behavior until it will approach the proportional limit, which is the end of that linear line here. So this is the proportional limit of these materials. So when subjected to torsion, this is the material's shear stress where it is still going to behave elastically. So according to this region here, we'll also follow Hooke's law. The shear stress is proportional to the shear strain. And here, the shear modulus of elasticity is the slope of this linear line. And the ultimate shear stress is at this point here, and here is where the material is going to fail. The shear stress that caused these materials to fail. So now let's have a brief discussion on hardness tests. So materials in many applications, component that you are designing and not only required to them to be with higher strength, but sometimes you also need the materials to have high wear resistance. So wear resistance is when you subjected materials to friction, it won't wear. So it will keep the material surface as it is. So we need a lot of materials, we need a lot of application, we need the material surface to be very hard. So for example is when materials, the components are moving and in contact with each other, such as gear, shaft, bolts and pins. So you need the surface of these materials to be having higher hardness. So hardness test, you can use hardness test to measure the material resistance to plastic deformation. For example, to indentation or scratch. So hardness test, the purpose of hardness test is this, is to find out what is the material resistance to the surface resistance to plastic deformation. There are a few hardness tests to measure materials resistant to localized plastic deformation. And the first one that I'm going to introduce is the Rockwell Hardness Test. So this is how the Rockwell Hardness Test is being conducted.
Hardness test is used to test the hardness of a material by indentation. This machine here is a CV600A, which is a hardness tester, and it's got two scales. It's got the scale C and scale B modes. Scale C uses a diamond indenter like this one. It measures materials like quench steel, tempered steel, more of the harder materials. Whereas the scale B measures aluminium, alloys, copper, malleable cast irons, but that one uses a steel ball indenter. Material like mild steel, this is used as a calibration test piece to check that the machine's in working order and is up to calibration. It's got numbers written on here that specifies its actual hardness. This is mild steel, so we'll be using a scale B indenter with a steel ball. So firstly, you want to put it into the holding chucks and tighten it with the knob provided. Okay, next we want to put the workbench that we'd be putting the specimen onto. These can come in various different shapes because you might have a rod that you want to try and test. So with a B scale indenter, first of all you have to apply a minor load and then a major load. The major load has preset settings on the side of this machine, and we just make sure that it is reading 980. You have a specification sheet that shows you the loading, the minor and major loadings of different scales. Next we'll put our test specimen onto the bench and use the feed handle to bring it all the way up to the ball indenter. Find a nice flat spot on the indenter and just let it touch the surface of the test material. By turning this feed handle, we'll apply the minor load by allowing the small needle to touch the red dot. So once that's there, we've applied the minor load. As we're using the B scale indenter, we have to look at the inside reading of the dials. So we want to position the big needle so it hits 0 on the red scale. This machine is hydraulically controlled, so it's got the major load configuration setting here. So once you've applied and calibrated the dials, you can apply the major load by simply just pushing it down. Then you wait for the needle to settle.
And release the load.
From this specific test that we've done now, we have this material and it's given us a number on the B scale. That number represents the Rockwell hardness number. It's also very good to do this test 3 to 5 times just to get a good average for the hardness of the material. Thanks for watching.
Alright, so from this video, you can see that in this test, hardness number is determined by the difference in the depth of penetration resulting from the application of initial load followed by the larger major load. So the minor load establishes the zero position. The major load is applied and then removed while still maintaining the minor load. The depth of penetration from the zero is measured from the dial, on which a harder material gives a lower measure. So the penetration depth and the hardness are inversely proportional. So another type of hardness test is brittle hardness test. So this test is done by forcing the hardened steel ball, as what you can see in this schematic here, under a known load into the surface of material that you are going to measure. So the diameter of the indentation after you unload it, you will have to see it under the microscope. So the brittle hardness number is expressed as the ratio of that indentation of the load with the area of indentation. So there is another one hardness test that we call as Vickers hardness test. So in this test, using an optical method, the size of indentation left by the indenter is measured. So the larger the indent left by the indenter at the defined test force in the surface of the material means that the material is softer. So those are some of the mechanical properties that you must know as a mechanical engineer. So by learning about the mechanical properties, you know that in each materials there will be a certain limit where elastic behavior is going to be reached, to be bridged. So it's at certain limit. If I applied force to this material, it's going to generate the stress that it's going to cause these materials to yield. So you don't want that. So that's why you need to learn about mechanical properties of the materials. So that as an engineer, you will be a designer. So you will be a design engineer. So when designing the structural member or mechanical element, the stress in it must be restricted to a certain safe level. So now that you know, like for instance, I have mild steel. The yield strength of this mild steel is 250 megapascal. And if I want to design the shaft using this mild steel, I cannot apply torque to this material that will cause this shaft that will cause stress to generate to this yield point. I need to have a lower allowable stress. So you need to have a factor of safety. So you need to choose allowable load or allowable stress that is much lower than what the member can fully support. Because you always have to remember, you always have to allow some accidental load. And therefore, we always need to have factor of safety. So factor of safety is equals to the load where it's going to fail divided by the allowable force. Or if we're talking about stress, it's the yield strength divided by the allowable stress. So the summary for this topic. In this topic, we have learned that engineering stress is defined as the instantaneous load divided by the original specimen cross-sectional area. So the engineering stress and strain curve is actually the stress in the y-axis is the formula is the instantaneous stress always going to be divided by the cross-sectional area. The engineering stress is expressed as the change in length divided by the original length. It's always going to be relative to the original length. The stress and strain curve is an important diagram to obtain a lot of mechanical properties of materials. We've also talked about Poisson ratio, and we've talked about hardness test, and there are different types of hardness tests which is used to measure the material resistance to localized plastic deformation. Now I'm going to continue with the second part of this module 5, in which I am going to talk about material failures. The learning outcome for this particular lesson is that by the end of this lesson, you should be able to describe the mechanism of crack propagation for both ductile and brittle mode of fracture. Another objective for today's module are to understand why is it critical in design to know if a material is going to behave in ductile or brittle manner, and to understand the importance of the ductile to brittle transition temperature. And also you need to be able to define fatigue and creep failure and specify the condition under which they can occur. So these are just some classic examples of material failures that can cause catastrophic failure. So when an engineer did not have any or did not have a strong material science knowledge, something like this can happen. So with Titanic, what happened was the steel that was used to build this ship is actually a steel that can transform or transform its behavior when it's at higher temperature to lower temperature. So at lower temperature, this materials is brittle. At higher temperature, this materials is ductile. So this steel that they use is having this behavior. So when they built this ship, the temperature was higher. So it is behaving in a ductile manner. But when it was in service, when they use it and the water temperature was really low, that steel transformed to become brittle. So when it is impacted with that iceberg, I hope you all have seen the movie Titanic. So when it was impacted with that iceberg, that materials is now brittle. It cannot absorb a lot of energy. So what happened is that crack that exists in the hull of that ship starts to propagate instantaneously. So what happened is that materials break into that ship has break into two, because that steel that they use to build that ship is transforming itself from being ductile at higher temperature to being brittle at lower temperature, and it cannot absorb more energy. So another example is this, can't remember the name of this building, Glen Tower building in UK. So they're using polymer material as cladding materials, but because they choose these materials because it's non-combustible. So when fire happens, it's not a combustible materials. But with polymer, we know that when it's being heated up, it is going to soften. So it is going to behave like liquid. So even though it's not combustible, what is going to happen is that it's going to be an agent to cause that fire to move from one place to another place. So it behaves like liquid. So that's why this fire has spread all over because of that cladding. So I hope you can see by now how important it is, this topic, for you as an engineer. So it's for you to avoid this kind of failure when designing anything. So in a nutshell, fracture is the separation of a body into two or more pieces as a result of imposed stress. So the usual causes of material failure are incorrect material selection, incorrect processing, incorrect manufacturing procedure, inadequate design, or incorrect use. So in this lesson, we will talk about some of the fundamental of fracture and what can cause fracture. Any fracture process involves two steps. The first one is crack formation, and the second one is the propagation of that crack in response to an imposed stress. So for metal, two modes of fracture are possible. One is ductile and another one is brittle. So ductile fracture happens in 4 steps. So the first step is the initial necking. So this is where the material starts to deform in a non-uniform manner. So plastic deformation happens in a non-uniform manner. And the second step, after necking starts to, you can start to observe the non-uniform plastic deformation, cavity will start to form in that region. And this cavity will form a small crack. And as the stress being imposed and it's not being taken away, what is going to happen is that these cracks will start to propagate. And finally, the material will fracture. So if you observe the fracture surface of ductile materials, when you fracture it and you observe the fracture surface under the microscope, so this is the example of scanning electron microscope image. So what you can see, the characteristic of this fracture surface is that it contains a lot of spherical dimples. So this is a characteristic of ductile fracture. So you can also determine whether the material is ductile or brittle by looking at the fracture surface. So with ductile fracture, you will observe a lot of plastic deformation on the surface, and the characteristic is that you will have a lot of the spherical dimple. So with brittle fracture, the fracture surface of the brittle failure is usually reasonably smooth. So brittle fracture exhibit by low plastic deformation. So the crack will propagate through the material by a process that we call as cleavage. So the atomic bonding between two atoms will be severed. So there are two ways that materials can fracture in brittle manner. One is what we call as transgranular brittle fracture. So in transgranular brittle fracture, the materials, the crack actually propagate through the grain. So as you can observe here, what you can see is that the fracture surface did not have a lot of plastic deformation as the one that you can see for the ductile fracture. Another mechanism of brittle fracture is what we call as intergranular brittle fracture. So with intergranular brittle fracture, the path of the crack propagation is through the grain boundary. And this is the scanning electron microscope image of intergranular brittle fracture. You can see also for this one, the fracture surface is quite smooth if we compare to the ductile materials. So far, we have learned that material can be ductile or materials can be brittle. So materials like ceramic, we talk a lot about it, that it's brittle materials. Once it reaches tensile properties, it's not going to deform plastically, it's going to break straight away. So this is a characteristic of brittle materials. Another example of brittle material is gray cast iron. So they cannot absorb a lot of energy. What is going to happen is it's going to break straight away when it reaches its tensile strength. And for ductile materials like mild steel, we know that it is going to behave in a ductile manner when it fractures. So it will, you can see a huge plastic deformation before it starts to fracture. So it means that these materials can absorb a lot of energy before it fractures. But at low temperature, some metal can transform to become ductile, brittle. So the materials that would be ductile at room temperature can become brittle. So this is known as a ductile to brittle transition. But to understand this transition, we first need to understand impact testing. So to get started, there's something material have which called as notch impact energy. And what notch impact energy is a measure of the energy required to fracture a notch sample of a material. So one impact testing that material scientists use to measure this notch impact energy is Charpy impact test. So what happens is the testing engineers will take small sample of material with a notch in the middle, and they will impact the material with weight on the pendulum. And it will come down and it will hit the material. And utilizing this test, they can measure the amount of notch impact energy that the material has. And if a material has a lower impact energy, it behaving in a brittle manner. And if it has a high impact energy, means that this material behaving in a ductile manner. So let's think about why is this important? Why does engineer care if a material is ductile or brittle in design? So I want you to pause this, take a few minutes and think about that. Why do we care if it's going to be fail in a ductile manner or if it's going to be fail in a brittle manner? So a designer cares if a material is ductile or brittle because brittle failure are catastrophic and they happen with very little warning. So like the US World War II tanker here, and you can see here what happened with the Titanic happened with this as well. So the hull is almost cracked directly in half. So this was a catastrophic failure and it occurred with no warning, and it is a brittle failure because ductile failure you can inspect it. So when the materials behave in a brittle manner, you can see that it starts to deform. But with brittle manner, you cannot see it. It is going to just happen instantaneously. So you will start to see with the brittle manner, you will start to see some yielding or deformation. But with brittle failure, it is a rapid fracture. And so designer have to be very aware if the material that they are going to use in their design is going to behave in a brittle or in a ductile manner. And so that's why we have this impact energy test. It is to determine if our impact energy is over the high side here, which means that this material is going to be ductile, or you're probably going to have an impact energy on the lower side here. So this means that your material is brittle. But toughness is not constant for a given material, but they varies largely with temperature. So if let's say I run an impact test for a particular materials, at a lower temperature, that material that material at lower temperature behave in brittle manner. But as I keep increasing the temperature, I test the same materials, but I test it at different temperature. That materials become ductile. So for some materials, you will see something that we call as ductile to brittle transition temperature, where at certain temperature, the material starts to behave in a more ductile manner, and you will see that impact energy increase, and at lower temperature the material will behave in a brittle manner. And typically, you will want to operate above the ductile to brittle transition temperature. So the materials is behaving in a ductile manner. So the classic example of ductile to brittle fracture is the Titanic. And this is the same as this example here, the World War II tanker that you can see here. And you can see this tanker split in half. So it had been actually in the water for almost a year. It had just finished its sea testing and it was sitting at the harbor at the Atlantic side of the United States. So the water there is much cooler. And all of the sudden, the crack just propagated through almost the entire hull. So what initially was thought was that these materials, this hull had a series of bad weld joint. But actually, this ship was built in the Pacific side of the United States, where the water is much cooler. So when it was built, the steel exhibit ductile behavior. But when it was docked in the Atlantic side, the water is much cooler and therefore the materials transition from being ductile to brittle. So this is the failure when they observe it is a brittle failure. To begin with, this material, this steel that they use is a ductile steel. So materials can change its behavior when temperature change. So you must be aware that this kind of failure can happen. So with different type of materials, by doing impact testing, we can determine whether they're going to change their behavior depending on temperature. So another type of failure of materials that can occur is when it is in service is fatigue failure. So fatigue failure happen by formation of crack and its propagation due to repetitive or cyclic loading. So normally most fatigue failure are caused by cyclic loading that is significantly low than the yielding of the materials. But because these materials has been imposed by this cyclic loading over and over, even though the stress is low, but because of that repetitive load, it can cause failure as well. So fatigue failure happen after a number of cycles of that repetitive load. So there are 3 stages of these cracks to happen. So the first stage is when the crack starts to initiate. So normally it will initiate at the surface of the materials. So let's say you have a scratch or something on the surface. It's an imperfection on the surface of the materials. So after a certain cycle of that cyclic loading, so this is the cycle, after a certain cycle, that crack starts to grow. And it will go to a second stage where the crack propagation will be in a steady state. So as the number of cycles of that cyclic loading increase, that crack will start to grow and it will start to propagate. But it is in a much lower rate. But after that crack reaches a certain length, which is the critical length, it will start to, after a certain number of cycles, it will start to propagate and it will start to break suddenly. So that's the 3 cycles of fatigue failure. So one classic example of fatigue failure is the de Havilland Comet, which entered service in 1952, and they become the first commercial airliner to be powered by jet engine. So unlike most prior commercial aircraft, the Comet operated at altitude where the aircraft cabin need to be pressurized. The pressurization of the cabin resulted in the stress in the skin of the metal skin of the aircraft, and the cycle of the cabin pressurization and depressurization during each of the flight resulted in small crack at the square corner of the passenger window. So over time, so we know that when it's square dimension, stress will be concentrated at that point. All right. So over time, the crack that was formed at that corner of the square window reach its, so every time it takes flight, it will pressurize and depressurize, pressurize and depressurize. So this is a cyclic loading. So over time, the crack grew and reached a critical size. And once it reached its critical size, it propagated catastrophically, causing the breakup of the aircraft in mid-flight. So you should go and read about it and see how interesting that this kind of case study. So a lot of case study has been done to understand certain accident, and most of engineering accidents are caused by lack of knowledge in materials science. So just like the other mechanical properties, we can also conduct fatigue tests to tell us the behavior of these materials, any materials, under cyclic loading. So fatigue tests can provide us with a number of key properties of the material under investigation, such as its fatigue life, its fatigue strength, and its fatigue limit. So this is a usual setup for fatigue testing. So if you are interested, there's a lot of video in YouTube where you can see how this test has been performed. So what they did during this testing is that to apply cyclic loading, applied cyclic loading to the materials, and they will use for the same materials, they will perform a different test with different cyclic loading to tell that at certain loading, what is the cycle that this materials is going to fail. And if I use another intensity of that, if I increase the intensity or if I increase the applied load and I impose this load in a cyclic manner, what is the cycle that will cause these materials to fail? So they will perform this testing on the same materials with different intensity or with the different applied load, and they will test it until it fails, and they will calculate what number of cycles that these materials fail under this load. So that is how fatigue testing is being performed. So using fatigue testing, we can plot this diagram. So this is what we call as SN curve. So this curve is the stress versus the number of cycle. So this is an SN curve of brittle aluminum with an ultimate tensile strength of 320 megapascal. So they have performed this test for this material several times under different load. So they have found out that at the force that will cause 300, that will generate the 320 megapascal, they only need one cycle and this material is going to fail. And when they perform the test that will generate the 300 megapascal stress, it will break after 10 cycle and so on. So they've performed another test with the cyclic load that will cause about 260 megapascal stress. It's going to fail after 100 cycle. And they keep reducing that force, and they found out that this material has a fatigue limit. So if the stress is low enough, it will generate a stress that is at that value. No matter how many cycles, these materials won't fail. So that is what we call as fatigue limit. So I have this suggestion of fatigue testing video in YouTube. Go and have a look how they perform this test, and it will tell you how they plot this SN curve diagram as well. So another type of deformation or material failure is creep deformation. So creep is a time-dependent deformation under a certain constant applied load. So generally it occurs at high temperature, but it can also happen at room temperature in certain materials. But this failure, when it happened at room temperature, it happened at a much slower rate. So as a result, the material will undergo a time-dependent increase in length. So at high temperature, normally even metal will be softened, and both their yield strength and their tensile strength will decrease. So at elevated temperature, materials can lose their elastic limit under constant load. So the material will lengthen, and this elongation is irreversible because they're now going to deform in a plastic deformation over a longer period of time. So no matter how low is the tension that you have applied to these materials, when creep happens, this deformation cannot be reversible. So creep happens at an elevated temperature where diffusion process takes place. So vacancy, as you have learned before, can move at high temperature, and this will cause the dislocation to climb. So I have this video here to show you how this mechanism can happen. So as you can see, at an elevated temperature, vacancy can move, and from this video here, you can see that the dislocation can climb from one plane to another. If, let's say, for an instant, that to begin with, this dislocation has been pinned by an impurity atoms, so that impurity atoms prevent it from moving. But because at high temperature, it can climb from one plane to another plane, that dislocation pin is no longer effective. So that materials can now deform. So this deformation is irreversible even though at low stresses. The rate of deformation is called the creep rate. It is the slope of the line in the creep strain versus time curve. So the primary creep happens, or it starts at a rapid rate and slows with time. And as the time continues, secondary creep will happen, and it has a relatively uniform rate. And tertiary creep has an accelerated creep rate and terminates when the material breaks or rupture. So creep failure is one of the most important failure modes for turbine blades. So turbine blades is exposed to higher temperature all the time. So it is one of the most common failure modes of turbine blades. Another example is this big dip ceiling collapse tragedy. So what happened was that they used an epoxy to anchor this bolt. And this bolt has been exposed to constant load all the time, and this epoxy eventually, over time, at higher temperature in that tunnel, has experienced creep deformation, and eventually it breaks and the whole ceilings collapse. So in summary, in this lesson, we have learned that fracture may occur by ductile and brittle modes, where both involve the formation and propagation of cracks. It is also possible for material to experience a ductile to brittle transition when the temperature changes from the higher temperature to low temperature. And also another type of material failure is fatigue failure, which is common type of failure that is caused when an applied stress level fluctuates with time. And we also have a time-dependent plastic deformation of material which is subjected to constant load and temperature, and it is termed as creep deformation. So that's about it for this lesson. Thank you for listening.